3 million acres. That is roughly half the size of Vermont, and it is how much of Oregon and Washington has burned this summer. As I record this, there are more than 50 large fires still active across the two states. The National Preparedness Level is at 5, the highest there is, meaning the country's firefighting resources are fully committed. It is the highest acreage burned in the Northwest since at least the year 2000. On one day last week, another 150,000 acres went, double the previous day's total. And around Spokane, the 3 fires that took more than 700 structures at the start of this month, Old Trails, Autumn Lane, Fairview, are now all at 97% containment, effectively finished. So across the Pacific Northwest right now, everyone is waiting for the same thing. Forecasters say there is some moisture in the region over the next 2 weeks, though no significant rain in the immediate forecast. Oregon's fire season traditionally ends the way it always has, with the first proper rains, usually in late September. That is the shift. It is coming, and everybody wants it. Here is my question, and it is the reason for this video. What happens to 3 million acres of burned ground when the rain finally arrives? Because the answer is not what most people assume, and it is not a story that will be covered when it happens, because the cameras will have gone. I will answer it properly, which means going through what fire actually does to soil first, and it is stranger than you would guess. No guessing, no dramatizing, just the numbers, the mechanism, and the stakes. Before we start, if you are in Washington, Oregon, Idaho, or British Columbia, tell me in the comments where you are and what the air has been like, because a lot of people watching have been breathing this for weeks. Subscribe if you want the plain version of these, and a thumbs up helps. Let us go for 5,000. Now, let us get into it. First, why this year? 2 conditions set it up, and neither is about ignition sources. The Northwest came out of winter with record low snowpack. Snowpack is not just water storage, it is a schedule. Mountain snow melts gradually through spring and early summer, keeping soil and vegetation damp well into the dry season. Take the snow away, and the drying starts earlier and goes further. On top of that, an ongoing drought. Fire officials have said plainly that the combination left live and dead fuels critically dry across the region, which accelerated curing, the process by which living vegetation loses moisture and becomes fuel, and enabled aggressive fire behavior even without the usual alignment of fuels, weather, and topography all lining up. That last clause is the one that matters. Normally, a big fire run needs several things to coincide. This year, the fuels were dry enough that the fire did not need the rest of the setup. The result, by the numbers as of yesterday, the Big Grass Fire in Malheur County, Oregon, at 579,000 acres, 34% contained. The Sinlahican Fire in Washington at 153,000 acres. The Little Giant Fire at 127,000 acres and only 5% contained. Washington's governor has declared a statewide wildfire emergency, with a burn ban running through the 30th of September. Now, what fire does to the ground? And I want to start with what an unburned hillside does with rain, because you need the baseline. On healthy ground, rain does not simply land and run off. The canopy intercepts a good share of it and lets it drip through slowly. The litter layer on the floor, needles, duff, decaying wood, breaks the impact of the drops that get through and acts like a sponge. Below that, roots hold the soil together mechanically, and old root channels and animal burrows give water a path down into the ground. So most rain goes into the hillside rather than across it. A vegetated slope is not just held together by roots, it is plumbed. Fire removes every one of those layers at once. Canopy gone, so raindrops hit bare soil at full speed. Litter gone, so nothing absorbs them. and the roots begin to decay over the following seasons, so the mechanical reinforcement fades on a delay. But the thing that happens inside the soil is the part almost nobody knows about. When vegetation burns, it releases waxy organic compounds, the same class of compounds that make a leaf shed water. Intense heat vaporizes them at the surface. But soil is a poor conductor of heat, so a few centimeters down it is still cool. Those vapors move downward into that cooler zone and condense there, coating the individual soil grains. What you end up with is a layer buried a small distance below the surface that actively repels water. Not as a figure of speech, physically. You can dig into a burned slope, pour water in, and watch it sit there in a bead rather than soak away. Soil scientists call it hydrophobicity, and the foundational work goes back to Debano in the 1970s. It is not the only pathway either. There are 3 recognized ones, and they usually act together. The second is that severely burned ground gets extremely dry, hyper dry in the literature, and soil in that state resists wetting on its own. The third is pore clogging. Ash and fine particles wash into the gaps between grains and physically seal the surface. Any one of them reduces how fast water can enter the ground. Together, they can nearly stop it. So picture the slope now. No canopy, no litter, roots dying, and a water-repellent layer a couple of centimeters down. Rain arrives, saturates the thin skin above that layer almost immediately, and then has nowhere to go but sideways. It becomes overland flow, a sheet of water moving across the hillside instead of into it. That is the whole change. The hillside stops being a sponge and becomes a roof. Now, a sheet of water on a bare slope is not yet the hazard. What matters is what it picks up. Fast water over loose ash and soil, with no roots and no litter holding anything, entrains sediment. And as it entrains more, it gets denser and heavier, and a denser flow can carry still more. It feeds itself. Past a certain point, the mixture stops behaving like muddy water and starts behaving like wet concrete moving downhill. That is a debris flow. It carries boulders and whole trees. It arrives as a front rather than as a rising level, and it can move faster than a person can run. There is a distinction here that gets missed constantly. Most post-fire debris flows are not landslides. A landslide starts as a mass of soil that detaches and slides. These start as runoff, water moving over the surface, gathering material as it goes. Researchers call them runoff-generated debris flows. That matters because it means you do not need the slope to fail. You only need enough water moving fast enough over enough loose material. And it means the warning signs are different too. A slope about to slide sometimes gives you cracks, tilted trees, seepage. A runoff-generated debris flow gives you nothing. The hillside looks exactly as it did yesterday. What changes is the sky. So how much rain does it take? The U.S. Geological Survey models this with a standard design storm, and the one they use has a peak 15-minute rainfall intensity of 24 millimeters an hour. That phrasing hides how small the number is, so let me convert it. 24 millimeters an hour, sustained over 15 minutes, is 6 millimeters of rain, about a quarter of an inch in 15 minutes. That is the design storm. A quarter inch of rain in a quarter of an hour, landing on a burned slope, is enough to be modeled as a debris flow trigger. And the USGS chose that figure deliberately because it is ordinary. A burst of that intensity has roughly a 1 to 5 year recurrence interval across most of the western United States. Not a 100-year storm, a normal thunderstorm cell, the kind that turns up most summers, and one known to have triggered debris flows at USGS monitoring sites in burn areas. The key variable is intensity, not total. Researchers focus on peak rainfall intensity averaged over 15 minutes because short bursts are what generate runoff. An inch of rain falling gently across a day may do nothing at all. A quarter inch in 15 minutes can start a debris flow. Same total, delivered differently, completely different outcome. There is a second variable that matters just as much, and it is the slope itself. The hazard models use a threshold of 23 degrees, not because anything magical happens at 23, but because it is roughly where gravity's pull along the slope surface becomes large enough relative to the friction holding loose material in place that water-saturated debris will keep moving once it starts rather than coming to rest. Below that, material tends to stall out. Above it, a flow that gets going can sustain itself down the channel. And this is why moderate to high burn severity on slopes over 23 degrees is the phrase that does the work in every one of these assessments. Not acreage, not flame height. The specific intersection of badly burned soil and steep enough ground measured basin by basin. 100,000 acres of severe burn on flat rangeland is an ecological event. 10,000 acres of severe burn in steep terrain above a valley road is a public safety problem for the next several years. Washington has a team for exactly this. The state's Geological Survey runs WALERT, the Wildfire-Associated Landslide Emergency Response Team, sending geologists into severely burned areas and, importantly, downstream of them, using LiDAR and imagery to find evidence of historical debris flows and identify what sits in the path. Their own framing is that after a fire, even modest amounts of rainfall can produce dangerous flash floods and debris flows. They have already done this in Washington recently. After the Cedar Creek fire, the assessment found 3 debris flows and 2 hyper-concentrated flows, that is, the in-between category, more sediment than a flood, less than a debris flow. One of those debris flows deposited about 14,000 square yards of gravelly sand and woody debris across an agricultural field. 2 others silted up the irrigation ditch feeding the southwest Meadow Valley. That is what a moderate post-fire event looks like on the ground, not a movie. A field buried and a ditch that no longer carries water to the farms that depend on it. Which brings me to how anybody knows which hillsides to worry about, because 3 million acres burned is useless as a hazard statement. What matters is how it burned and where. The term of art is soil burn severity, and it is not the same thing as how much vegetation was destroyed. A fast-moving grass fire can blacken a hillside completely while barely heating the soil beneath it. A slow, hot fire in heavy timber can leave the ground sterilized to depth. From a helicopter, both look burned. Only one of them has had its hydrology rebuilt. The first pass at measuring it is done from orbit, and the technique is elegant. Healthy vegetation is highly reflective in near-infrared light. That is what makes plants look bright in false-color satellite images. Bare soil, ash, and char are comparatively reflective in shortwave infrared instead. So you take the ratio of those 2 bands before the fire and after it and difference them. Where that ratio has flipped hardest, the ground has changed most. The product is called a bark map, Burned Area Reflectance Classification, and it can be generated while the fire is still burning. But it is a reflectance measurement, not a soil measurement. A satellite cannot see 2 centimeters down, which is precisely where the water repellent layer lives. So a BEAR team, Burned Area Emergency Response, goes into the field and validates it. Digging, testing infiltration by pouring water onto exposed soil and timing how long it takes to penetrate. Checking root structure and ash depth. They correct the satellite classification where it is wrong, and what comes out the other side is the soil burn severity map. That is the document that actually matters, and it is the one to watch for on these fires. There is one more consequence worth knowing because it affects far more people than live on the slopes themselves. Burned watersheds do not only send debris downhill, they send sediment and ash into reservoirs and river intakes. Water utilities downstream of large burns routinely face increased treatment costs and, in bad cases, suspended sediment loads beyond what a plant is designed to handle. The Methow irrigation ditch is the small version of that problem. The large version is a city's drinking water supply. And there is a timing detail inside all of this that I find genuinely unsettling, so I will give it to you straight. The water repellent layer is at its strongest immediately after the fire, and it breaks down over months as soil organisms, freeze-thaw cycles, and root growth work it apart. So on that measure, the hazard is worst in the first wet season and declines from there. But root strength runs on the opposite schedule. The roots of burned vegetation do not fail on the day of the fire. They decay. Mechanical reinforcement of the soil holds for a while and then falls away, typically reaching its minimum somewhere in the second to fourth year before new root systems have grown enough to replace it. Two curves running in opposite directions. Peak water repellency early, minimum root strength later, which means there is no single season you can point to and say the danger has passed. The mechanism that dominates simply changes. Right, so we have the mechanism and we have the trigger. Let me now answer the question. What happens when the rain arrives? The rain is not relief. It is the second event. And there is one case everybody in this field refers to, which I will state plainly rather than luridly. In December 2017, the Thomas Fire burned a large area of hills above Santa Barbara County, California. It was contained. As far as most people were concerned, the emergency was over. On the 9th of January 2018, about a month later, an intense rain cell moved over the burn scar above Montecito. Debris flows came down the canyons into the town. 23 people were killed. More people died in the debris flows than died in the fire that made them possible. And the fire had been out for weeks. I am not raising that to frighten anyone in Washington or Oregon, and the terrain and rainfall patterns here are not Southern California's. I raise it because it is the clearest demonstration of the thing this whole video is built on. The fire is an event with an end date. What the fire did to the ground is a condition that persists, and it persists far longer than people expect. The USGS is explicit. The debris flow hazard remains elevated for 2 to 5 years after a fire, declining gradually as vegetation returns and soil structure recovers. Washington's team says the same, elevated for several years. So run the timeline forward. The fires get contained, as Old Trails and Autumn Lane and Fairview just did. The smoke clears. The news moves on. The evacuation orders lift and people go home. And the hillsides above those neighborhoods stay loaded for the next several summers, waiting for a wet afternoon that nobody will report in advance. Now, one thing I want you to know how to read, because assessments are coming. When the burn severity maps and hazard assessments come out for these fires, you will see two things modeled for each drainage basin. The likelihood that a debris flow starts there in response to the design storm, and the potential volume of material. The likelihood model is a logistic regression built by Staley and colleagues in 2016, combining the three things we have already covered: severity, slope, and soil erodibility, each multiplied by the rainfall of the design storm. It is not a guess. Now, the limitation, which the USGS states openly in its own FAQ. The maps do not show run-out paths. They model where debris flows start, not where they go, how far they travel, or what they hit. Modeling run-out through populated terrain remains an open research problem, which means the maps can tell you that a basin above a particular neighborhood is likely to produce a debris flow, and they cannot tell you whose house is in the path. That gap is not a failure. It is the honest edge of what this science currently does, and it is exactly the qualification that gets rounded off when a hazard map reaches the news. So here is what to do, and it applies anywhere downhill of a burn scar. Work out whether you are below a burn scar, not just in one. The hazard travels. Washington's team routinely assesses areas downstream that the fire never touched. Watch rainfall intensity, not forecast totals. Half an inch of rain tells you almost nothing. Whether it lands over 6 hours or 15 minutes is the entire question. Expect no warning from the ground. These start as runoff. No cracking, no creaking, no slow tilt. If you are told to leave during rain, the reason you are told early is that nobody can tell you late. Know the sound. People who survive debris flows consistently describe hearing it before seeing it. A deep, sustained rumble, boulders knocking together inside the flow. If you hear that below a burn scar in heavy rain, go uphill and laterally out of the drainage, not downhill and not along it. And put 2 to 5 years in your calendar, not one wet season. The shift is coming. The rain will arrive, and it will end the fire season, and it will clear the air, and for a few days, it will feel like the end of the story. 3 million acres of the Pacific Northwest are now waiting underneath it. Tell me in the comments where you are and what the air has been like. Subscribe if you want the follow-up when the burn severity maps publish, because that is the one I will be reading. And thank you for giving me this much of your afternoon. I will see you next time.